test. Sound test. Come on. Why is the quality so weird? Oh no, that's much better. That's a different plane today. So you guys, welcome to the level 3 version of Mathdemic. So this is, today we're just going to be kind of looking at trig proofs and modeling, because that's what some of these guys actually asked for. Again, I've not actually taught this standard since 2016. That's a long time ago that I've actually taught the standard, but I'll tell you what, I still remember a few things that I can kind of pass on to you guys. From memory, I just want to kind of, before I do my from memory, I just want to welcome Mr. Dama here, who is actually a good mate of mine, who's also another teacher. Really good to see you here, mate. Why is it named Mathdemic? Well, pandemic, man. During pandemic, you're learning some maths, so hence Mathdemic. I gotta give credit to my wife for that name. Cool. So the first thing I want to spend some time doing is kind of working on just coming up with an equation for a sine graph, because from memory, I believe that if you are doing the trig modeling part of things, you kind of need to learn how to do a sine graph, or come up with an equation for a sine graph. Just kind of basically start out with. Salty, you just kind of answered the question there. It's £1 each. Neither. All right. So with your sine graph at the moment, like I want to see if I can get rid of this. Now, I think you guys would have actually learned it in like so many different ways within your classroom, because every teacher has their own style of doing how they come up with the equation, or how they actually teach you guys as well. All right. Now, I know that some teachers like to do things like, to find out amplitude, they look at the maximum and minimum of the sine graph. Yes, this is for the trig internal mica for level 3. So I kind of will be doing both. I'll be doing the modeling aspect and the proof aspect as well. So just to kind of start off with, the way I like to work with a sine graph is this. And again, you guys can choose to work with this. If you're happy with the sine graph modeling and you know what you're doing, then that's absolutely fine. You don't really have to follow this method. But this is something that I kind of messed around with some of my students, and it pretty much helped them out. So to kind of get started, what I tend to do is, like, the formula that I like to work with is this. Y is equal to a sine 2 pi over, what color am I going to choose here? And then we shall have HQ, x minus h. I need a different color. Let's go pink. So this is, yeah, these streams will always be saved, guys, so don't stress about it. Like, you can always come back later and have a look at it as well. So everything will be uploaded. So this is the generic formula that I like to work with. And I know some teachers, they work with different formulas. They'll have like A, B, C, and D, and so on. It really doesn't matter, guys, because at the end of the day, no matter what graph you end up, what equation you end up using, as long as you can get the same graph as what you're trying to model, then you're pretty much good to go. So the next thing, what I like to do is, like, I just look at the main part of the sine graph, because I know that a sine graph looks like this red line here, right? But what I tend to do is that I literally create like a 4x2 box. Okay, what I mean by a 4x2 box is, I'm getting all these things kind of popping up. Hang on. So this is what I'm talking about. I create a box like this. Okay, because this just helps me kind of like visualize the sine graph itself. And then what I do is I kind of start looking at the lengths of these boxes. All right, what I mean by the length again is that in this particular case, if you look at it, this part here is 3 units. Like it's, well, not 3 units, it's like 4 boxes high. So this tends to be the amplitude. Now the period is how long it takes for one cycle. So that's the length of this entire box. That's going to be the P right there. And finally, the H and the V, that is where my sine graph is actually starting. So that's this point right here, the yellow point. The yellow point is going to be my H and the letter V. Okay, so that's pretty much kind of like the base idea that I start out with. All right, so anytime you see a sine graph, you kind of convert the sine graph into a 4x2 box, and from that you should be able to extract all the information you need to try and get the equation for this graph. So what I've done is I'm just going to kind of drag another picture along so that we can kind of see what I mean by, and hopefully it works. So as you can see right now, I've got a kind of like a sine graph that's kind of just, you know, it's repeating itself, it's starting off and it's kind of going along. So what I'm going to do is I'm going to try and create this 4x2 box where it has the sine graph. Now if I look at it, the sine graph, the part that I want starts from here and goes all the way up till 25. All right, that's the part of the sine graph I want to be looking at. So I'm going to create this little 4x2 box. Just kind of drawing it out. I'm going to get rid of this 5 there. There we go. I just want to see those numbers there. So there's my 4x2 box. So at this point, I can actually work out what the amplitude is, because I can see that the amplitude is starting from 2 and it's going up to 6. So the amplitude A is going to equal 4 units in this case. Next, I want to have a look at the period. So the period is actually the start of the sine graph all the way to the end of the sine graph. And if you look at it, it's actually going from 5 to 25. So that means the period equals to 20. Pretty much you got it right there, Friction. So Shaq, this is the thing about, I know I just saw you retract that message, but the way you look at how the sine graph starts is because the shape of the sine graph always looks like this. So that's how you know that the starting point is always that little yellow spot that I've actually covered there. So that's that point there is going to be H and V. All right. So in this case, our H and V is going to be this yellow point, but I shouldn't have. I'm just going to get rid of this. Oh, no, I'll leave it there. It's fine. This point right here is going to be your H and V, and you can see that that point right there is 5 and 2. All right, So that's it. You've got the equation of this graph right now, because now you can actually say, what happened to my colors? Oh no, they all changed. I just realized my entire color scheme has changed there. Oh, that sucks. It's all right. I will rewrite that equation. That's fine. Stupid thing. So here I'm going to have y is equal to a is equal to 4. Then I've got sine 2 pi over p, which is 20. And then x minus 5, double bracket, and plus 2. Just going to write this equation again because the color changed. So y is equal to a sine 2 pi over p x minus there we go. Sweet. Is that kind of makes sense for you guys? So so anytime you get like word questions, right? Like, you know, you get things like Ferris wheels and like what else that I can think of, like water spouts or whatever, you know, or waves, whatever you can think of, right? If you can actually draw the sine graph, just a rough sketch of it, and then just wrap that 4x2 box around it, then you can pretty much get all the information that you need. Friction, you don't need to actually work out x because you're giving the equation of the sine graph. Remember, like when you give equation of a straight line, you just write it as like y equals 2x plus something. You don't really solve it. Jonesy, I haven't done it since somebody else was asking me that before. I was telling them I haven't done scholarship calculus since Fast and the Furious Tokyo Drift. So that's a long time away. Can you cancel out the 4 and 20? No, you cannot cancel out the 4 and 20. The reason is the 20 is actually inside the sine function. So you can't just go ahead and cancel it. So that's like you asking me this question where if I say something like y is equal to 4x squared, that's like you saying, oh, I can actually cancel out the 4 and 2 to write this as 2 and 1. You know, we don't actually do that. So we just kind of leave it as it is. So yeah, because that 20 is actually inside the sine function. Make it 2 pi over 5. I could leave it as 2 pi over 10, not 2 pi over 5. Okay guys, so what I'm going to do is I'm going to give you guys a little sine graph for you guys to try and do by yourself. So let me just get a graph for you. -2 settings x-axis. Sweet. All right, I'm going to put up another question for you guys. Hopefully there we go. Why don't you guys have a go at question 1 there? I hope you guys can actually see it on the screen. Let me just check it out. Okay, now you can actually see the graph. I was actually worried that you won't be able to see the graph. Do we just leave the 2 pi over time period factored out? Yes, you can just leave it out like that. You don't need to simplify it or anything like that. it still would be working out the same way, even if you expand inside the bracket. So I'm going to put up 2 questions for you guys. I put up question 1 there, and I've just got to do question 2 for you guys as well. So you guys have a go with question 1. And if you want to check your answer, whether you've done the right thing, what you could do is you could actually put it in your graphics calculator to check it. Or you could also put it in, I mean, because if you guys are right now using, if you're on your computer, obviously, you could actually just go to Desmos and just put your equation in there just to see if it actually works out. All right, I'm just going to put up question 2 for you guys as well, so you guys can have a go at that. TS, I'm not doing any domain and range yet in this. I'm just kind of going through the questions as they are. So I want you guys to have a go with question 1 and question 2 by yourself. I'll give you guys, I'll give you guys a few minutes to just kind of have a go at it. And it's all right if you make some mistakes. You know, we kind of learn from our mistakes, and just have a go. Most important thing. Hey, Salty, we're just doing some basic trig graphs, sine graph really. Yeah, I'll give you guys another 90 seconds, then I'll get started on this question. Both TS? Yes, Jonesy, you could potentially do that as well. There's nothing wrong with that. Yeah, you can actually do that as well. And I'll come back to that in our next session, like how the difference between a sine and a cosine is just 90 degrees. Cosine is basically just shifted 90 degrees to the, I always get confused, to the right or to the left. I can't remember off the top, but yeah, it is just like shifted 90 degrees to one side. Uh, yeah, TS, your question is, I had a look at it, man. Like, yeah, I'll show you how easy it is, that question. You're gonna get really super annoyed with it when you actually look at how to do this. Don't worry, Salty. We're gonna go through this answer right now. All right. Ugh, oops. Never throw your stylus on top of your thing. But anyway, question one. So what we're going to do is we're going to look what's the best part of the sine graph that we want to actually start with. See you, Mr. Dama. It's good having you here. So at the moment, remember that the sine graph, you want to actually start from the middle of it, right? So if I look at it, like kind of like looking at these points right now. So this is going to be 1. That's at -5. Now, let me just zoom in a bit more so you guys can see better. Okay, so because that's at 1 and that's at -5, I kind of know the middle of this is going to be at somewhere here, which is going to be -2. So the sine graph is actually starting from here and it's going 1 cycle up to there. Internal, man. So I'm going to create my little box around this. All right, it is going to be a 4x2 box as always. I think I messed that up. Really messed that up. Sorry, guys. Thinking about something else and just started messing around with this. That's not where the middle is. This is the point I want to be doing it at. And the next one is going to be here. There's my 4x2 box. Cool. So once I have my 4x2 box, I can see what my amplitude is. I'm just going to copy that formula down. Where is that formula? There we go. Let's bring that down there. So we can see that the amplitude is this right here, which is going to equal to 3. Then I've got my period, which is from here to here. And you can kind of see that this point here is going to be 4. This point here is 20. So our period is going to be 16. Then our starting point, which is this yellow dot right here, that's your H and V. And in this case, it's going to be 4 and -2. So we've got all the information that we need, and so we can actually write our equation. So it's going to be y is equal to 3 sine 2 pi over 16 x minus 4 minus 2. TS, your question would come in an internal, but I don't think you'll get a question like that in an internal. It's just like they wouldn't ask a question like that. But before I move on to the next question, can I ask you guys, are you guys all good with question 1 here? Tears, Matt. You'll never have to thank. It's all good, man. Yeah, we'll do some compound angles. I actually enjoy doing the trig proofs. It's something I miss doing. Sweet. That's it. 1 yes. I can go on to question 2. By the way, guys, if you want to access these notes, they are available. Just go to the description. There is a link for this notes, so you can actually access these notes and it'll be available to you all times. All right. So it is under level 3 Mathdemic, today's session. So you can actually find it, because I know sometimes I like move screens and some people are still working on the previous screen. So yeah, you guys can actually go to the link and just follow this one note. Sweet. Let's go to the second question. I'll bring this sucker right now. So cool. So this next question, you kind of can actually do this question with 2 different starting points. All right. What I mean by 2 different starting points is, I mean, you might have actually did this as your starting point and kind of finished up here. That's one possibility. Or you might have actually started from here. All right. And I'm going to tell you guys this right now. It doesn't matter which starting point you actually choose, because a sine graph actually repeats itself. So you could have chosen any of these 3 red dots here as your H and V, and they would all still be the same answer. All right. So it doesn't really matter which where you put your H and V. Yeah, so that's what I wanted to start off with. So I'm going to start doing the light blue one. So I'm going to get rid of this. I'm going to get rid of my red dots there. So I'm going to start with this, and I'm going to start creating my little 4x2 box. There we go. Now this one's a bit funny because it's like is kind of going halfway, so that's all right. We're just kind of going to make it have to go halfway too. There. And hopefully you guys can actually see my 4x2 box right there popping up. Okay, so we start working the amplitude. So for the amplitude, this value here is 8. This value here is 3. So we can say that the amplitude is going to equal 5. Next thing is looking at the period. So for the period, this is 8. This is 15, 16, 17, 18. So the period is equal to 10. And as for my H and V, the starting point, which is this one here, I'm going to go with 8 and 3. Okay, so got my equation then. So it is y is equal to a, which happens to be 5, sine 2 pi over, what's my period, 10. And I've got x minus 8 plus 3. Revish, yes, we'll be doing, continuing with the bit of trig on Monday for level 2. Okay, now I just wanted to show you guys another thing here. All right, I hope this would work, but like, remember I told you that there's the 3 red starting points. Like you could have actually have this point here, which is 18, 3, or you could have actually had this point here, which is minus 2, 3. All right, so that means you potentially could have got 3 from this picture. You could have actually got 3 equations. So you could have 5 sine 2 pi over 10, x minus 18 plus 3. Or you could have had y is equal to 5 sine 2 pi over 10 x minus negative 2 plus 3. But the negative negative makes it a positive, so I'm just going to rewrite that as plus 2. So what I want you guys to notice is, notice how the amplitude is all the same, all right, because it's the same graph. If you look at your period, that's all the same as well, all right, because it's the same period. It just repeats after the same cycle. The vertical shift, that's how much it's moved up along the y-axis, that's also the same. It's always going to be 3, 3, 3. But the horizontal shift, notice the difference between these three numbers. Okay, what I want you guys to have a look at is that the part where I've actually colored in green, those numbers, there's a difference of 10 between them. Because think about it, if I have minus 18, minus 8, and positive 2, what's happening is, this thing is annoying me, get out of here. That the difference between these are plus 10, plus 10. So that's where that 10 period comes from. No, Shaq, with this modeling, you really want to be working with pi. You don't actually go with degrees at all. No, you don't actually go to degrees at all, because most of your graph modeling that you do is in real world, so you do not actually go near degrees at all. Just stay with radians. Yeah, you're right. So that's where that period actually comes from. Like, so see, I should actually put this in a different color. So it doesn't matter which of those red points you actually start with, because it has a period of 10, you know, it's just going to keep cycling like that. I mean, like, you literally can come up with like unlimited equations with this model, because what it does is that it's just that the green number that I've highlighted in green just increases by 10 all the time, and then you come back with the same equation. Well, I hope that I don't have to do this next year, Revish, because I really don't want to be doing quarantine maths. But I actually don't teach senior college, man. I actually am working in junior college, so I don't really mess around with internals. I only do the external tutorials. But all this stuff is going to stay here anyway. It's not going anywhere, so you can always come back next year and access this. All right. Are we happy with this, or do you guys want to do another sine graph question? Or do you guys want me to actually show you how the cos one works? And TS, real quickly, to answer your question, the one that you sent me, I would say if you go to your formula sheet and go to, wait, I'm just having a look. Where is that? No, that's not it. Yeah, if you go look up compound angle formula TS, the question you sent me, theta is actually equal to pi over 3 plus pi over 6. Because if you look at that tan formula, it's literally the same thing as it is. Did you still want me to show it to you? Just let me know. Otherwise, friction, you want to see cos. I'm happy to show you guys how the cos graph actually looks like. Same rules, exactly the same rules for cos. There's only one minor change to it, that's all. Okay, so let's actually try and do cos at the moment. So I'm going to actually go back. By the way, all of these 4 graphs that we've actually done, we're actually going to use the same graphs, but we're going to actually do cos. Yeah, I'd like to do it, Angie, but like I'd have to start from the beginning, like in the sense where, actually, you know what? Should I do cos now or do some proofs? Friction, I'm going to show you cos real quickly because it only takes about 2 minutes to show you cos. If you understand sine, you're going to understand cos. Let me show you what I mean by. Because for cos, all you have to do is this. I need a graph. Yep, I'm just going to show you guys cos real quickly, and then we shall move along to the next one. So the only difference, friction, for cos rule is this. The cos graph looks like this, right? So that's the only part we're going to be looking at. Like that. All right. So the only thing though is your h and v now is this point right here. 1, 2, 3, 4. No, that's not it. Because I'm going to draw my little square, like the 4x2 rectangle. Just bear with me, guys. So yeah, this is all that there is for cos. So all the rules that you did for sine is exactly the same thing that you do for cos as well. So that means your a value is still this part right here, from here to here. Your p value is from here to here. And your h and v is the same thing as we did before. That point right there is going to be h and v. Something's not right here. Yeah. Yep, friction. So it's exactly the same technique. And yeah, so that's all causes. You just look at the different part of the graph, and you can actually remodel it as a cos graph. So that's why I don't really bother spending too much time with cos graph, because if you understand sine graph, then you understand cos graph. It's just the way it is. So yeah, those are the 2 things that you guys actually need to know for your basic trig modeling. And then later on, we'll actually have a look at some multiple solutions of how to do that part of it. We'll actually do it later on next week sometime. Yes, I'll be doing that, Revish, once the schedules are out. Yep, good night, Salty. Get you up, man. It'll be up here. Yeah, friction, it is. Like, and I think if you remember, somebody asked earlier about one of the questions, can I just do like a minus cos? I think, what was it? was question 1 here. You know, you could do that as well. So yeah, that's just the same kind of ideas. Are we happy with sine and cos? And can we move on to some trig proofs? Because clearly a few people are still kind of hanging around for the trig proofs. No, TS 2 pi generally means it's like one cycle. So yeah, it just stands for one cycle. That's why you'd never actually go away from 2 pi. Cool. So what I want to do for trig proofs at the moment is, like, there's a couple of basics that we need to do first, all right? Once we do the basic trig proofs, we could actually move on to some of the more trickier ones. So can you do complex numbers, Johnny? Sorry, man, Johnny, I think I've got a lot of people wanting trig proofs. I might see if I have some time later on. We can sit down and see if who wants to do complex numbers. Cool. So just to kind of get started with trig proofs, let's actually get rid of this. The first one that I'm going to do is real simple. I mean, like, in the sense where you guys don't have too many identities, just kind of messing around with your basic few identities that you got to do, the simple identities. All right. So the first thing to remember is you've always worked with sine x, cos x, and tan x. All right. Now, a couple of things to notice is that there is a brand new kind of inverse ones that actually pop up, which is cosec x, sec x, and cot x. So with cosec x, it is just the inverse of sine x. So it's just 1 over sine x. Sec x is 1 over cos x, and cot x is 1 over tan x. So that means we can also say that tan x is 1 over cot x, and cos x is 1 over sec x, and sine x is 1 over cosec x. Now all of these things are actually, I believe it's given to you guys in your formula sheet. All right, so those are some of the first basic ones that you need to know. The second basic ones that are worth knowing is this one here. Sine x over cos x equals tan x. That's a pretty useful one. And also sine squared x plus cos squared x equals to 1. All right, and the last one that's super useful is, we kind of talked about it like just previously in our graphs. Like, you know how I talked to you guys about how sine graph and cos graph is the same graph and it's just shifted by 90 degrees. So that's something useful to know, which sometimes is not given in the formula sheet, but it's basically, it looks like this. But again, we hardly use this one. The most important one that we use is basically, well, actually everything except, maybe I should do it this way. Give me a second. The one that we don't really use much is this one. Not as much we don't use, but the rest of the other nine of them, we actually use quite a bit of it. So one thing about trig proofs is this. You usually end up with a right-hand side and a left-hand side, and you kind of have to prove that one side is equal to the other side. Okay, so just to kind of start off with a real simple question. Now, some of you guys might have actually done these questions because, you know, it is quite common, these questions. But I'm going to start out with sec x times cot x. And then we've got to prove that it's equal to cosec x. Now, notice these 3 lines. Really important that to understand those 3 lines there. Those 3 lines mean that it's not that they're equal to, it's just that it's the proof. Do we have to know double angle? Eventually you will need to know how to do that as well. We will spend some time doing some double angle proofs as well. Double angle proofs, double angle is actually very good to know, because if you're doing integration for calculus, it definitely comes in handy. Like this. Okay, so what I'm going to do is, for this question, I want to actually eliminate the left-hand side. I want to actually simplify left-hand side to equal the right-hand side. All right. So what I've got here is I've got sec x and I've got cot x. Okay. One more little formula that'll come quite handy for you guys is actually rewriting cot x as also cos x over sine x. It's a very handy one to actually kind of have. No worries, Ravish. See you Monday. So because I've got sec x is equal to 1 over cos x. So you guys can see that here. So I'm going to replace that with 1 over cos x multiplied by cot x. Cot x is equal to, now as you can see, there's actually two versions of cot x. So I could actually do 1 over tan x, or I could do cos x over sine x. All right, I'm going to use the cos x over sine x. And that's what I end up with. Now you can kind of see that the cos x, they cancel out each other, and you're left over with just 1 over sine x. And if you go back to the proofs, we need to look at what 1 over sine x is equal to, and that's cosec x. So what we've done is we've actually proved that the left-hand side is equal to the right-hand side. Sweet. I'm going to put up a question for you guys to try and have a go at. Unfortunately, I've kind of colored this all in, but yeah, it's all right. Okay, you guys try and have a go at this question here. And guys, if you do have any other proof questions that you want me to go through, just drop it in any of my socials or in the email, which is in the description below, in the video itself, video description. So if you do have a particular proof you're struggling with, just flick me a message somewhere there. All right, I want you guys to have a go at this one. Tan x times cosec x, and all of this is equal to sec x. A good way to start these questions is like having a look at on that right-hand side to see what you need to end up with. So that means you got to look at that left-hand side and go, well, what are all the things I can actually change or get rid of? You guys are doing number 2 friction, question number 2, which is here, highlighted in yellow. You guys can try and prove this. Sweet. Friction, I'm going to go through this question at the moment. So tan x, what we have is tan x is actually equal to sine x over cos x, and then cosec x is 1 over sine x. And what I can do is I can get rid of the two sine x, cancel out each other, and I'm left with 1 over cos x. And of course 1 over cos x is sec x. And now that's actually all equal to sec x. Yeah, so pretty kind of like easy start right there. You all good with that, Friction? Cool. What I might do though is I'm just looking at. Okay, I'm gonna give you one more question. Oh wait, yeah, I'm waiting. For tan x, what did I write it as? Sine x over cos x? Because I used this one here, man. Because I know that I wanted to get rid of the sine x, because cosec is 1 over sine. Oh, no, I used, yeah, you're right. I mean, I could do it over 1 over cot x, but then what would happen is you'll go back and do the same thing again, because cot x is cos x over sine x and so on. Yeah, the thing about proofs is that like you can actually do it in like so many different ways, and you know, what you did was nothing wrong. It's just like an extra step, a couple of steps that you'd have to do with the way you did it. Okay, so do another easy one, or do another one, yeah? Very easy to get confused with these proofs, man. Okay, let me put up another question for you. So this one, we have tan x times cos squared x minus cot x times sine squared x, and we have to prove that this is equal to 0. Yep, this is the last one for us today. All right, I will work through it, okay? So if you look at it, tan x is actually sine over cos. So I'm going to write this as sine x over cos x times cos squared x minus cot x. I can write that as cos x over sine x. That's colored in pink. And this is all multiplied by sine squared x. Not going to worry about that equal to 0 part. So here I can cancel out 1 of the cos x from the numerator, and the same with the sine x. I could actually cancel out 1 of the sine x, and so what I have is sine x cos x minus cos x sine x. And because this is basically saying the same thing as sine x cos x minus sine x cos x, which is equal to 0, and therefore it's equal to 0 as well. Yeah, I absolutely enjoy doing proofs, man, because I mean, like, once you get some of the more harder ones, they just super satisfying when you actually try and get the actual answer. yeah, so I think it's good that you got to that first part and then just kind of trying to see like where you can actually make those changes. Friction, the more proofs that you actually do, the more practice you do, you start to recognize the patterns of how to actually eliminate things and so on. Initially at the start, it is a bit painful, but then because you're not making those connections yet, but once you start doing a few, you start seeing the connections, it actually starts making sense. Cool. I'm actually going to call it there, guys. So if you do have any final kind of questions, just pop it in the comment section. Otherwise, I shall catch you guys next week, I believe, on Tuesday. Then it's good for you, mate. Like, what are you guys doing at the moment? Are you doing complex numbers? Okay. Well, we can actually do some complex numbers next time because I think trigs, it's how do I say it? It's all right, but I do enjoy complex numbers as well quite a bit. Sweet, Friction. I'm gonna call it, mate. I think that's just us. No worries, get vexed. Catch you guys next week on Tuesday. Simultaneous equation. Good fun, that one. Alright, I'm going to end this stream, guys. Thanks again.